see my screen?
Yes, we can. Please.
Okay. Okay. So, hello everybody. Thank you so much for this opportunity to talk about my work. I am Gabriele Riccio, a second-year student, PhD student at the National Center of Nuclear Research. And today I would like to talk about a little bit of estimation of physical parameters, galaxy physical parameters, using LSST data. So first of all, let's do a little introduction on the Large Survey of Space of Time. It will be the biggest ground telescope, the biggest survey based on the ground telescope that we will have and will be released in about 2 years. So the main feature that I want to stress is that it will observe a very wide portion of the southern sky, about 18,000 degrees in 6 optical filters. So our expected terabyte and terabyte of data, so 15 terabyte of data every night. So we will observe a lot of objects, and more importantly, those observations will be very high quality in terms of magnitude. So for example, if we have to compare and consider the R band, they will reach depth of 24.5 for single images and almost 28 for full stacked data in 10 years of survey. So are very high quality of magnitude for a ground telescope. So it is interesting to work also on this observation to understand how can we use it to calculate things that we're interested in galaxies. So as physical parameters, I'm meaning in this sense like mostly star formation rate, dust luminosity, dust mass, stellar mass, things that we are interested on in the galaxy evolution and properties. So everybody here knows how works the star formation rate in galaxy. So what is important is that we have these very dusty these very dusty molecular clouds, and inside the star formation is happening. So what happens is that dust absorb this light from the young stars and remit in the infrared part. So if we want to probe the star formation rate, we must have information about the UV part of the SED of the galaxy. So we can probe the young stars and have a direct estimation of the star formation rate. But also the far infrared part is very important because it's the emission of this hot dust and is the missing part of the star formation rate, an hidden star formation rate that we need to have reliable estimation. So the interaction between star and dust is very important, but it's also very complex. So we know that there is a distinction between extinction and attenuation. And when we are going to study far distant galaxies, so high redshift galaxy, the attenuation is the things that we are interested in. Of course, it's very difficult to probe it because we don't know the geometry of the dust, we don't know the stars, how are distributed inside this dust. So what we can do is to choose attenuation laws to try to mimic the place, the role of this dust in what we are observing. And so there are several attenuation laws, as you know, Charlotte-Foulk, Alzetti, Lo-Faro, that can be used. So dust is important also, we know it. And so if there are other parts of the SED that dust affect mostly, and are the mid-infrared part that is mostly the PIH that are also linked to the metallicity that emits in this part. And also we have the cold dust in the sub-millimeter part of the SED that is a direct probing of the dust mass. So with this introduction, I want to stress that each part of the SED is very important to have a detailed description of the galaxy and to estimate the physical parameters. So why we want to study LSST and why we don't want to test, why we are testing LSST now before it's releasing. Because LSST will observe just here, they will be very high quality and we will see a lot of objects, but just optical, UV, and a little bit in the near infrared observation. So how can we use this observation to obtain good estimation of physical parameters? Also, before the release of JWST, so how to use just this without infrared, mid-infrared, far infrared, sub-millimeter observation. So to answer this question, we select a sample of around 65,000 objects over the redshift range of 0 to 2.5 from ELACE-N1 and Cosmos field of the HELP survey. So we use these real galaxies to both estimate what we consider real physical parameters. So we estimate those physical parameters using a full SED coverage to UV to far infrared in order to compare with the LSSD estimation. And also we use this galaxy as a starting point to simulate the LSST observation itself. We decided to use ELACE and Cosmos because are widely studied in literature, and so we know more or less how objects behave in these fields. So to estimate the physical parameters, we use an SED fitting method. We use SIGAL, Code Investigating Galaxy Emission tool. And to do that, we have to, of course, use some input parameters. Here is quickly what I used in my work. So a star formation history, we used, as we want to work only on main sequence galaxy, we have to discard all the starburst in our sample. So we use the delayed starburst plus burst star formation history to discard, evaluate and discard starburst, and then a delayed star formation history on the only main sequence galaxy because it's more suited to fit it. Then single stellar population as Bruce Wall and Charlot 2003. Attenuation law, we decide to use Charlot and Fall as it distinguish between attenuation in the bird cloud and in the ISM, so two different power law. And then as dust emission, I used Rayleigh 2014. So quickly our methodology. So how to evaluate the starbus? We just followed method described on Rodriguero et al. 2011. So he described, analyzed the specific star formation rate distribution of the sample. So he found that this distribution should follow a Gaussian. And so what we did is to fit this distribution with a Gaussian and define as starbus all the objects that are 3 sigma away from the center of the Gaussian. So in this plot are the object on the right of this black line. And so looking at the main sequence, we can see that the starbus that we evaluate in this way are in the place that should be. So it's a good evaluation. Also then, we have to simulate the LSST observation to work on it. So to do that, we use directly the SEDs. In fact, SIGAL has a module called fluxes that estimate magnitude, estimate fluxes, using as starting point the SED of each object and the bands, the filters that of course are provided by LSST. But we cannot use the errors that the Bayesian method gives us, that SIGAL gives us, because it doesn't take into account possible random effects that during an observation could happen. So for example, changing in atmospheric conditions, so seeing or something like that. Also some issues in the hardware. So what we did to simulate as much as possible LSST-like observation, we used this simulation, LSST simulation called CATSIM, that evaluate errors using as basis this formula. So here is taken into account through lambda and M5, the atmospheric condition and the hardware components, and also M here is the magnitude. So we define the magnitude that we use the magnitude that we calculated with SIGAL, and in this way we obtain these magnitude errors in function of the magnitude. So this catalog will be available online when my paper will be released, if you are interested on. So at the end of that, after we simulated the LSST observation, of course, we ran SIGAL with delayed star formation history on LSSD fluxes and estimated the physical parameters. So what we found, the results. First of all, I want to show you a comparison, SED comparison of the same object between the two runs, so LSSD here and the full observation coverage. And we can see that, of course, without the infrared part completely is another thing. The peak of the far infrared is completely different. But how it is translated in physical parameters. For this object, we have a comparable stellar mass, but different star formation rate. So to go deeper inside this, we look at the main sequence. We look at the main sequence. So we can see here that LSSD, that is in black, is not probing very well low star formation rate object. So that are here in gray, that are the old bands run. But this difference tends to disappear. The two main sequences tend to overlap, going to higher redshift. So how can we have an insight, a better insight in these differences? Of course, looking at the ratios between the physical parameters. Here we have the parameter ratio on the y-axis, defined as the log 10 of the parameter calculated with LSSD on the real one in function of redshift. And for the star formation rate, we can see, so on 0 is a comparable result. And so with star formation rate, we have a big overestimation at low redshift, so between 0 and 1.0, that decrease going to higher redshift. And fitting this trend, this overestimation with a polynomial function, we found this formula that can be used to correct the overestimation. The stellar mass instead is very well estimated, is around 0 at all redshift range. And in fact, because in general, stellar masses are evaluated with the optical and UV emission of the stars, and so well probed by LSST. Also looking at dust luminosity and dust mass, we have similar trend for as star formation rate. So dust luminosity share the same result, all the results that I will share with star formation rate, while M dust is slightly different, but still we obtain an overestimation. So how can we correct the overestimation? We could use the formula that I showed before, but we can also add some other filters to try also to understand where the problem is. So here are the same results as before, and we can see that adding far infrared spire observation and UV galaxy observation doesn't change so much. Galaxies change a little bit, but still we have an overestimation and also a strange trend between redshift 1. But adding mid-infrared Dirac observation, the star formation rate is completely corrected at all redshift, while the dust luminosity is corrected using the far infrared observation. Of course, because the cold dust emits in this part, and the spire covers this part of the SED, and so the M dust is well probed just adding spire observation. So as my time is finished, I will leave you with my conclusion, and thank you so much for your attention.
Thank you very much. We have 2 questions on Slack. So Tomo asked, why is the SFR ratio goes to 0 at redshift 1? And why does it correlate with redshift? And also at high redshift, UV bright galaxies have high SFR. Is that not true?
Yes. In principle, at high redshift, galaxies should have a higher star formation rate. Why the star formation rate goes to 0 going to higher redshift? We think that as we are moving to higher redshift, of course, our optical observation that are LSSD are like shifted in the UV part, because the rest frame is in the UV, but we observe it in the optical part. So what we are probing with LSSD at higher redshift is the UV part of the spectrum, and so it better constrains the star formation rate. So the comparison between the all band, having all band, and the difference between the all band run and the LSSD is like decreasing when we have a probe of the UV part with the LSSD. So we think that is this, and probably we will go into study more about that, because also adding galaxies, we obtain no overestimation in this, and galaxies like we obtain no correction in this, and galaxies near UV and far UV observation. So as galaxies, because here we did like cross match between our sample that is 65,000 galaxies with galaxies, and we just obtained 3,000 galaxies in this. So here is not like that, because here are around thousands and thousands of galaxies. Here are just 3,000. So we are not sure that we have the good statistics to understand this plot, and so probably in future work we are going to analyze more this trend.
See, the star formation rate from SED fitting is mostly from UV, right? And UV you do have from LSST optical, so I don't understand.
Yes, so we have just U band.
So if this is stellar mass estimate, yes, I understand, because at high G you don't have near infrared, so it's difficult to estimate stellar mass. But why star formation rate? It's almost going to zero.
Why star formation rate? I didn't understand.
Me neither.
Yes, I didn't understand the question. Why star formation rate?
Sorry. So maybe you guys can continue discuss on that.
No problem.
I had just one quick question. On this slide, does your correction depend on any other galaxy properties like size or surface density or color?
Yes, we tried to find the connection between physical parameters. For example, the trend with the colors, this trend with just luminosity. But I can show here. But there is no correction, no correlation. Mainly with colors. So I tried also different colors, LSST colors, these things, but I didn't find any correlation between them and other parameters.
All right. Okay. So I think we should move on. Thank you, Gabriele.